Swayam Prabha. Digital India. Educated India.
Welcome back to Mechanics and Control of Robotic Manipulator. Last few classes we have seen how to derive equation of motion, and in that two popular method we have seen. One is Lagrangian Euler, the other one is Newton-Euler. So the Newton-Euler, I said it is better for the computational perspective. So in this particular lecture we are going to see how to derive the equation of motion for given example using Newton-Euler method with the help of Matlab codes. So in the sense here we are going to see the Matlab session. So in that sense we will actually move forward. So we will be talking about dynamic model derivation using Newton-Euler method through the help of Matlab. So in the sense we would be straight away see the Matlab code, and then I will actually move to the Matlab environment. So in the sense, so this is the example which we have derived in the you can say regular lecture. The same example I am taking it for simplicity, but it is not going to restrict. You can actually use any you can say serial manipulator in this particular case. Only thing you have to change the DH parameter and then equation of motion in a series. So that I will show you in the Matlab session, but right now you can take it that a planar serial manipulator we have taken. So in that case, so what one can see, like if I know this M1, M2, and if I know L1 and L2, and I assume that theta 1 and theta 2 are the joint variable, I can derive the equation of motion with the help of forward propagation and backward propagation together. So for that I am rewriting that equation. So first what we need to know, so till now in velocity kinematics, so we have already shown how to derive, you can say, the DH parameter through the help of frame. Once you derive the DH parameter or once you obtain the DH parameter, you can substitute in one of the Matlab code. You can actually find the rotational matrix, rotational matrices and position vectors of the individual joints. These all we have seen. Further what we have seen, we can see how to propagate the angular velocity and linear velocity if we know the base angular velocity and linear velocity. So we always assume that the base is fixed. So these codes all we have seen in, you can say, the kinematic model derivation and as well as differential kinematic cases, or you call velocity propagation model. So in that sense, what right now we required what would be the centroidal location. So in this case the mass is, the link 1 mass is concentrated at the point J1, which is actually the mass is M1 and there is no inertia, it is a point mass. Similarly the second link mass is concentrated at M2, okay, or you can say J2 point as a M2. So in that sense what one is supposed to know, so if you recall your frame arrangement, so along L1 whatever that is assigned is x1 axis, along L2 that would be x2 axis. So now if I see the link 1, the centroidal location, so from frame 1 that would be actually like you can see along x there is a L1 distance, y and z 0 0, right. Similarly if I see the centroidal location of second link with respect to second joint or second frame, that again actually like along x2 only L2, all other axis is 0. So that is what we have actually derived. So here in our equation of motion we have written as link length as A1 and A2. So in that sense the location of what you call center of mass of link would be actually come with the two symbol, so which is LC1 and LC2. So here LC1 I consider as A1 and LC2 I consider as A2. So in that sense, so the PC1 and PC2 vector I have derived in this way, okay. So then what else you need? You need actually inertial and acceleration variable. So what we have seen so far is only up to velocity. So the inertial effect will come in this case only two masses, but the acceleration effect theta 1 double dot and theta 2 double dot. So that is what we have actually written in the Matlab code. But by default these are all real variable, not in complex. So then you better define that as a real, so that the conjugate term will not come when you are square or do some operation. So once these all defined, what we need to do, you need to actually like take the angular acceleration, then linear acceleration, then get the inertial forces and moments, right? So that is what we are trying to do. So now the angular acceleration can be written in this form, because this is having only rotary joint. The rotary joint angular acceleration given in this relation. So we are actually like writing the same thing in Matlab, the same form, because the angular acceleration at the 0th frame, we assume it is fixed. So it would be getting 0, 0, 0. Then we are actually like propagating the angular acceleration, we call AL, which is alpha equivalent. So alpha 0 we know, then alpha 1 we can obtain with the help of this relation. The same relation we have written it in Matlab syntax. So similarly alpha 2 we can get it. So alpha 3 there is no active variable, so you can see that the cross terms are vanished. So this is what alpha 0 to alpha 3. So now coming to the linear acceleration. So we know the rotary joint linear acceleration relation. So which would be having, you can say tangential acceleration, then the radial acceleration, and the previous joint you can say linear acceleration. So in that case, so we can actually like derive this equation in Matlab, the same form. So A 0 0 we know, which is again start from 0, but if you assume that this is actually like a vertical manipulator, then the gravity direction you need to mention. So I assume that the G is the gravity that is acting in y axis. So in that sense you can see, so A 0 is no longer 0 vector, so 0, G and 0. Okay. So now based on this equation I can derive, you can say the joint one linear acceleration second and the third one. So all linear acceleration I derived. So now what we need to know? We need to know A1C, in the sense the linear acceleration of center of mass of link 1 and center of mass link 2. So we call A1C and A2C. So this can be derived in this form. Okay. So for inertial force you need this centroidal acceleration. So we have actually like derived the AC1 and AC2, which is actually like based on this equation we have actually like written in the general syntax. So now you can see that this omega 1 multiply with, or you can say cross multiply with PC1 and PC2. Similarly alpha 1 cross multiply with PC1 and PC2, in the sense this is going to give a tangential, this is going to give a radial, and this is the joint linear acceleration. So in the sense it is very clear. So now once you obtain the linear acceleration of the center of mass of links, so then what you can actually like do, you can multiply with inertia. So here only mass, so that would give the inertial force. So that we have obtained. So now till this what we have done is the forward propagation. So now we will come back to the backward propagation, where we assume that end effector forces and moments are zeros, just for simplicity, but later on you can consider some vector also, but right now we consider this all actually like 0. So then you can actually like see this is the equation to back propagate. Once you know the end effector velocity and the inertial forces, then you can actually like back propagate. So now we have written this equation. So the similar way we can actually like do the backward propagation for the moments. So you can do it again, you can do n2 to 2 and n1 to 1, so that you can actually like derive. So in the sense you can do n2, n1, and if you want to have a what you call shaking force and moment, then you can actually like do it up to, you can say 0. This is actually like equivalent to shaking forces and this is equivalent to shaking moments. So once you all obtain what you required the joint arc relation. So for that we will use this. So the tau 1 is actually like, since the first joint and second joint as a rotary joint, so the n of the third term would be equivalent to the joint arc. So now we are talking about tau 1. So then n1 of the third term would be the tau 1. You can make a simplification, it will give a equation, and similarly tau 2 is actually like n2 of third term, in the sense z axis term would be equivalent to tau 2. This is very clear. So now we will actually like move to Matlab code, original Matlab code which we have written. Okay. So now this is the Matlab code which we have written earlier. So this is the direct kinematic relation. So we have taken as actually like symbols which is having a generalized symbol. Then based on your DH parameter we have derived the symbol, and since it is a 2R serial manipulator, the end effector frame is the third frame. So you have exclude 0, so then you have total number of frame is 3, and you can actually like give your DH table as per the derivation earlier. Then you know the arm matrix. I hope the arm matrix is non-standard form which we derived in the beginning of the DH representation. Then as usual the cell, and then you have derived, and you can actually like get up to you call the transformation matrix. Once you obtain the transformation matrix, what we have done, we have actually like tried to see the kinematic model. This is what we have seen in the direct kinematic method or direct kinematic code. So after that we have tried to do the velocity kinematics. For that we need to know the, you can say, rotational matrices and as well as position vectors we have taken, and we have started understanding that for propagation you need the velocity information. So here there are two variables, theta 1 dot and theta 2 dot, so that we have actually like derived. So then we have propagated based on the, you can say, the velocity propagation model. So initially we have done the angular velocity, then end effector velocity we obtained, then we have done the linear velocity propagation and the linear velocity of the end effector we have derived. Then we are coming to the dynamic model. For the dynamic model, what is the first step we did? We did the center of mass, or you can say location of center of mass. So that we have already derived. So that equation or that vector we have substituted here. So right now this you can say definition is not required, but if you want you can actually like even write LC1x, LC1y, LC1z. Similarly you can write in that. So these all you can write it in here. If you know the exact your what you call model, solid model, and you know the exact location of the center of mass, you can do it. Right now we have taken a line diagram, so based on that the PC1 and PC2 written in this form. Then we are going for a dynamic model. So the gravity is one additional acceleration, then you have two joint acceleration, and there are two masses. So here we consider only point mass, that's why the initial value is not coming, or you can say second moment of inertia and product of inertia are not coming here. Okay. So then we are actually like doing the angular acceleration vector. So where we can say alpha 0 to alpha 3 we have actually like used and derived. Then you can see the linear acceleration, we assume that the gravity pulled vertically act down on the y axis. So that is what we have actually like substituted. So in that sense you can actually like get the linear acceleration vector in a propagated model. Then we have actually like calculated the linear acceleration of the center of mass. Then we have calculated the inertial forces of the link. So far what we have calculated, these all linear acceleration vector of joints, and this is linear acceleration of center of mass. Here link has come. So now link inertial forces we have calculated. Now we are coming backward to the joint forces and moment. So that is what we are actually like starting with the end effector. Then the joint forces and moments we are actually like calculated. Then the third element of the joint moment, or you can say joint moments, that would be equivalent to your input. So that is what we have actually like derived. Further you want to write it in a matrix form, then you can actually like always bring this, you can say, further command called equation to matrix and then take the coefficient. So these all can be done, but right now you can see the tau 1 and tau 2 we you can say derive. So I will actually like run this code. I hope there would not be any error. So if we run, then it would be giving the output in the Matlab window. Okay. So you can see this is the your what you call you can say the kinematic model. Okay. And what right now we are interested is actually like try to find out what you call tau 1. Okay. So tau 1 is, you can see, right, you can write it in the same form, right, and similarly you can see tau 2. So I will just make it, so tau 2. So now you can actually like even cross verify these equations what we have obtained right now, the same thing what we have actually like obtained here also. Okay. So in the sense you, if you actually like go back to your equation, so whatever you have actually like derived for this particular system, so the same equation what we are actually like obtaining in the Matlab output also. In the sense, what the benefit, you can use Matlab for you can say deriving the equation of motion. So now we have actually like derived this as actually like very simple model, right. If you want to do it the same thing for more complicated, for example there is a inertia. Okay. So for example I am saying that the first link is having inertia. Okay. So in the sense I am saying that there is a only second moment is there. Okay. I say only link. So now what I got, the second moment of inertia is there. So now I am actually like saying that the product of inertia also there. Okay. Then y is at 1, right. So these all the terms I have actually like included, these all real variable. Okay. So for what we have taken the only inertial force, but right now I have inertial moment also. So in the sense inertial moment is actually like what? So you can write I. Okay. So I here is actually like the bigger matrix. Okay. So I can actually like write I1 is actually like you can write IXX, IXY, and you can write XZ, and since it is actually like a 1, so I will write it 1. In fact, we will put a minus sign here that you can actually like get it even in the unit itself. So now I am actually like writing this is a tensor. So what we can actually like write you can write XY1, IYY, and IYZ1. Okay. So then you have actually like IXZ1, IYZ1, and IZZ1. Okay. This is the inertial value. So now your N1. Okay. So your N1 would be I1 multiplied with alpha 1. Okay. In fact, if you strictly go, so it would become as you can see omega 1, you can say cross. So I will write it that itself. So cross of omega 1 into multiply with I1 omega 1. But anyhow, in this case, this will not give any term. Okay. But this will be actually like making sense. So now in that case, so what happened here? So in this case, it would be just added as so N1. So if I add this, so what you can see that inertial term all would be coming. So I just want to run this. I hope so there is no error. So I will assume that there is no error. So now if I see tau 1, you can see that I z terms all coming appearing, right. So the other product of inertias are not coming because it is in a plane, and your theta 1 dot, theta 1 double dot all in only you can say z axis. That is why you can see it is having only I z. So now if you assume that you have a link, that link is having even inertia which is mass not concentrated at one point, it is actually distributed mass, then you have a second moment of inertia that is also included. So now the similar direction you can actually like go further and further. For example, you want even further. So in the sense I want to add even N2, I can add. Okay. Or here actually like instead of you can say the location. So this location I assume that this is not A1, the mass is concentrated some location in x axis. Okay. So now you can actually like see this. So it will be actually like changed. So now I am running it. So now earlier what you can see, it's a product. So now that product is actually like modified. You can see, right. So that LC1 is actually like coming, and L1 or L2 is actually like going out. So here you can actually like see it. So this is the way we can actually like derive the equation of motion in Newton-Euler. Newton-Euler is easy because it's everything is actually like in sequence. Even you can do the algorithm based, you can write it in a recursive base, but recursive is actually like, although it is simple, number of code is very small, but I prefer to write it in a lengthy way. In that way, even if any minor mistake happen, that can be rectified. But if you write in a code in a algorithm base, if a small mistake happened, it is very difficult to find. And when you compare to Lagrangian Euler, this is very simple because you no need to actually like back and forth from partial derivative to time derivative. So anyhow, in the next lecture, we are going to see the what you call Lagrangian Euler formulation method using Matlab. The same example we will take. But right now, what you have seen is actually like how to use Newton-Euler method in the Matlab environment and derive the equation of motion. So probably in time permits, in the example class, we will see the same code, how we can extend for higher order system, in the sense higher degree of systems. So that we will see. Until then, thank you and see you. Bye. Take care.